Wait, just slideshow.
I'm taking this water. Huh? It's done, right?
This one.
So I should start, huh? Yeah. So very good afternoon to all, and thanks to C-DAC Pune for inviting me and to address all of you, to all the participants who have connected on web. Okay, this webinar where we will discuss about that means how we can use quantum computer and what are the key techniques, right? How quantum computer can be applied for solving some good computation problems. So the title of my talk is obviously a very generic, okay, where I will try to pitch on the pitch on basically the quantum computing, what is quantum computing, and how we can take the theories or postulates of quantum computing to get in solving some interesting computing problems with a stress towards machine learning. So this is the agenda of my talk today. So I will start with the basics, okay, where I will discuss about the qubit state space and operations. And then we will give a little bit overview of what is quantum computing as an architecture, right? What are that means how we can utilize it for computing. Then I will go with some very basic quantum algorithms like Deutsch algorithm and Grover's algorithms, though we know if we look into the quantum zoo, we have 200 plus algorithms there, right? But we cannot discuss those in this particular time. We'll try to just give some of the basic things where you understand that what are the novelty of these quantum techniques, okay? Then I will specifically focus on the quantum machine learning, which is now coming up in a great way, right? As machine learning problems are very attractive now, and we are applying it on multiple domains. So hopefully quantum techniques for machine learning will be very attractive for all of us. Right at the end, I will discuss about some of the example use cases which are existing, and also some of the tools or platforms. What the designers, the algorithm developers or designers of the quantum applications can use, state of the art simulation techniques or simulation platforms. Okay, right, and then I will conclude. So let's start. Okay, so this is the progress of the computing paradigm, which started almost 150. That means almost 100 plus 100 years ago, maybe 80 years ago, not 100. Yeah, sorry, that means almost 80 years ago, right? And we started with this mechanical computers, which were only sufficient to do the number crunching. Okay, but calculating the things. But then we came to the silicon age, where we still presently belong, and silicon is continuing for the last 60 plus years, right? And we know that due to the miniaturization of the VLSI process and technology and the design, we are at an age where we are designing transistors of the size 1.5 nanometer. Right, and that is giving us an enormous opportunity to develop large number of circuits on a small chip, right? And that is giving the power of multi-core, the SoC, the neuromorphic computing, and the memory. Okay, what we have now. But if we are going farther, and what we are trying to move forward to the computing paradigm called quantum computing, what we show in the extreme right, where we try to define computing in terms of the atomic and the subatomic states of matter. Okay, why this is, I will gradually tell. But if we try to come from silicon to quantum computing, why it is? Because one is obviously the miniaturization of the size, right? The transistor presently is almost one atomic layer. Okay, so why cannot we try to build some computing using atom itself, or the atomic states itself? The main push of this quantum computing, or what I say, the main or one of the strongest push from quantum computing came in 1980, where Richard Feynman in his very historical lecture at MIT. Okay, so he said that at that point of time, quantum physics was very strong, right? A lot of research activities, a lot of experimentation were being going on in quantum physics, and Richard Feynman said that if we try to understand the quantum physics well, or try to utilize quantum physics well, the computing what we require should be quantum computing, because quantum computing works on the theory and the postulates of quantum physics. Fine, but those were the two drives, right? One is miniaturization, and one is that, hey, we have to simulate, we have to understand the quantum systems which are working and which are upcoming. But apart from these two basic push, the other strongest push came from what I will discuss today in my lecture in the quantum algorithm. The strong push came from the algorithm researchers like David Deutsch, Richard Joyce, Peter Shor, Love Grover, right? What they said that, it's not only that we are going quantum due to miniaturization or trying to simulate quantum physics. Quantum computing, quantum postulates, or that means are exploiting this quantum phenomenon of the matter. And if we can do computing with those particular, keeping those phenomena in the quantum domain, we will also get a speed up. Okay, so these are the main three things, right? What attracts quantum computing and what actually drives that, why we are trying to see a new paradigm of computing, and what I will discuss today. So now, if we try to look into the that means the classical computing and quantum computing, keeping them side by side, what we see, obviously we can say that it is not a winning for quantum computing. Obviously there are some winning, but there are also some challenges. So let's look into the first, that what are the fascinating things what happens in the quantum computing. So we know that the classical computing, right, is basically dependent on the interpretation of the data, right, and the data storage and data update. And data is stored basically in two basic symbols. One is the 0 symbol, right, and one is the 1, whose electrical analogy so 0 means a logic low voltage, and 1 means a logic high voltage. And we know that these are the two states, by which we can encode the data, and that is the way we actually represent it in the memory, and we do an update of the data, which is a part of computing, by changing the data from 0 to 1 or 1 to 0, right? When we look into the equivalent data form in the quantum, what we tell is the quantum bits or qubits. And qubits have the specialty that apart from having the two extreme states, so when we say qubit states, 0 and 1 becomes the two extreme states of a qubit, right? Having said so, obviously a qubit can exist in more than more number of states, not only 0 and 1. And what are those states? If I only focus on a single qubit, those states will be a sort of probability. We'll have a probability of being 0 or probability of being 1. The states of 0 and 1 can be taken as a probability of 1 is 1 and probability of 0 is 0. Right? And for the case of the state 0, the probability of 0 is 1 and probability is 1. But we can have all other states which can have a probability of 0 single qubit states, which can have a probability between 0 and 1 of getting measured at 0 or getting measured as 1, right? And all those states are the superposition states. And these the existence of superposition states, which is very inherent of the quantum mechanical energy states or quantum mechanical spin states or quantum mechanical polarization states of a photon, makes the qubit working with qubit and storage of data very different, what we do in the classical computing, right? And this particular phenomenon of superposition actually gets into the next point, which is the computing capacity. Okay, so if you were looking into a classical computer at present, suppose I have a 16-bit microprocessor and I need to make it a 32-bit microprocessor, what I need to do? Okay, I need to make a 16-bit microprocessor. We have to extend the register by 16-bit. We have to extend the data part by 16-bit. We have to extend the ALU functional blocks by 16-bit. So what it means that if I have to move from 16 to 32-bit processor, I have to add up 16-bit resources more in all the processing pipeline, right? So what it means that it's a linear. So what I add, I get. Find that amount of computation, I get more. So it's a more or less the linear to resource. Okay. But if you are looking for a quantum, that if you're going for a quantum computer, due to this superposition, what I do, if I try to make a 16 qubit or a 16 state computing, right? Okay, we use 4 qubits, right? And if I move to 32 state computing, I require 5 qubits. Okay, because why? Because an n qubit quantum system can represent 2 to the power n basis states. Okay, so each qubit I add, I actually increase the data capacity of my system, and also we will come to later the functional parallelism in the system by exponentially. Okay, which means that this gives us an enormous computing capacity with a much lower resource than what we get in a classical computing, and that is obviously a very that means very fascinating thing. But having said so, it is we have to remember that it is not that all the classical computing algorithms can exploit this particular phenomenon of quantum computing, and we will come to that pretty soon. Now, the area of concern, what needs to be addressed, or where obviously there are concern, is the fragility of the quantum states. Okay, because as we know that these quantum states are very fragile, because they are actually the states which can be only discovered when we go into the very finest level of the matter. Okay, so when we go into the finest level of the matter, right, the interaction of those finest levels with the other energy, okay, right, with the nearby atoms are also very strong, right? And it's very difficult, okay, to generate a high quantum volume, right, which are perfectly, sorry, switch it off, sorry. Yeah, so it's very difficult in that level of matter to isolate it from every other, that means every other matter, right, which are also there, they're in the lowest level, in the lowest form, right? And those interactions at that level of matter is very difficult to isolate, right? And due to this, lot of errors and noises can appear in a large scale quantum system. Okay, right? And for this, we are still restricted. As you know, that presently we are in the quantum system called NISQ, which is a noisy intermediate state quantum computing, which means that due to an higher error rates or noise, we are limiting our quantum computing into small scale quantum computer, right? And we cannot use many of the error correcting techniques, which requires a high redundancy of the qubits and increases requires a good number of qubits to encode those errors, and those cannot be utilized still. Okay, but obviously we know that from the technology point of view, a challenge, right? A challenge is a push towards discovery. So we all hope, and we have already seen that the milestone what has been set in the number of qubits are increasing in a very good rate, right? When it was started, we had only qubits which are of number of tens. Okay, now we have qubits which are almost hundreds, right? And there is a promise, right? We will be having 1,000 and 5,000 and maybe 10,000 qubits maybe within the next 5 to 8 years. Okay, so this is obviously taken care by a lot of engineering, a lot of engineering techniques and engineering theories are developed, the control theories are developed to handle this type of large number of qubits. But this is obviously still an area of concern, right? And the last thing what I mentioned earlier is that when we try to look into an algorithm and try to look that, hey, this can go into the quantum, right? This is a decision which needs to be taken very judiciously. It's not a thumb rule that every algorithm in the classical domain, find like every algorithm in a classical domain cannot be parallelized. Okay. Similarly, every algorithm in a classical domain might not have a speed up in the quantum computing. Okay. So we have to have a suitability or analyze the quantumness of an algorithm, and that analysis will lead us to find out or explore that okay, what is the suitable quantum system this algorithm can go for, or at all this quantum okay, this algorithm is suitable for any of the quantum systems. Okay, so what I now get into this a very simplistic or the very fundamental view of a quantum system. Okay, to introduce the quantum system, the first understanding should be to introduce a single qubit state. Okay, the single qubit state space. Okay, so Bloch sphere is a representation of a single qubit state space of a quantum system, right? If we can understand a single qubit quantum system, then we can easily extrapolate it, or we can easily find out how a multi-qubit quantum system can work. Okay, so what I show here is a sort of a quantum state which is represented as a psi. Okay, now this sphere is a Bloch sphere. A sphere means it has three axes. Okay, the z-axis, the x-axis, and the y-axis, which are also shown in this figure. Right. If you look into the z-axis, you will find that, as I mentioned when I tried to establish what is a qubit. Okay, the two extreme ends of the z-axis are marked with 0 and 1. So 0 and 1 are the quantum states. Also, I have to just introduce one notation here. You see that there is a way of representation of the quantum states, which is a sort of angular brace, right? And this is called the Kate notation. So this is used because many of the time in computing, we can have classical and quantum states which are handled together. Maybe a part is handled by classical and part is handled by the quantum system. Okay, so to identify distinctly that, okay, this particular state is a quantum state, we actually use this notation, which is called a Kate notation. So wherever we find a Kate notation and a symbol, we will try to get that this is a quantum state. Okay, so now let's come back to this again. So the z-axis has two extreme quantum states. One is the 0 and one is the 1. Okay, which means that, okay, these are the very fixed state of our single qubit system. I mean, these are always can be measured, right? We can always measure a qubit as a 0 or a 1. But what happens when the qubit is on the surface of the Bloch sphere? So the arbitrary state psi, which is shown in this particular figure, is a state on the surface of the sphere, right? And this particular state can also be imagined or also can be considered as a vector which starts from the origin and touches that point on the surface of the sphere. Right now, let us see a particular state space of any system, right, is modeled by the state variables, right? And what are the state variables for a single qubit system? The state variables for a single qubit systems are two parameters. One is a theta and one is the phi. Okay, there may be different interpretations. Maybe there are other interpretations, but what I find, this is the simplest interpretation, which is very easy to understand a qubit system. Okay, so the two state variables of a quantum single qubit quantum state are theta and phi. What is theta? Theta is the angle which this particular vector makes with the z-axis, right? And what is phi? Phi is the angle which this particular vector, with the projection of this vector on the xy plane, makes with the x-axis. So what is the state update? So now if we move this psi from a point on the surface, what is being shown in this particular figure, to another point, what it means that either I have changed the theta or I have changed the phi, or I have changed both of them. Okay, so the movement so now the entire movement of this particular vector across the sphere can be easily can be encoded or easily can be understood by the amount of change which has been done either on theta or on phi or on both, right? And that right and also one good thing is that means if we want to transform transform the quantum state, what it means, quantum state transformation means we are actually changing this vector psi, the orientation of the single qubit psi, right? And the way we do it are basically with the gates which rotates this across the various axes, right? And that's why when we look into the next discussion, we will come to the Pauli gates, which are the rotation gates, and how rotation gates affects a single qubit quantum system. Okay. Now, what I show next is the different values of theta and phi, which actually makes this vector align to very well demarcated quantum states. It is not that when we operate, we will only move into these quantum states, but some of the quantum states are very well demarcated, like the plus and minus. Plus and minus states are nothing that, okay, the states of the extreme in the x-axis. Like 0 and 1 are the extreme states of the z-axis. Plus and minus are the extreme states of the x-axis. So you see that from the z-axis to x-axis, orientation towards x-axis can be easily done by changing the theta and phi, right? And those who know QKD or have studied QKD, you know what we do in QKD. That means in QKD we randomly orient this particular basis basis of the qubit state, so that we cannot we don't know that where to measure this qubit. So we'll come to the measurement also, right? And then we show plus I and minus I. Plus I and minus I are the extremes of the y-axis. Okay, so you see that different values of theta and phi will lead to some of the very well demarcated quantum states which are across the axis, and also any arbitrary quantum state, okay, with some arbitrary values of theta and phi. So we move across, okay, right, and we play across, okay, this particular thing, right? Okay, so the generic form is expressed at the first line, which is psi equals to cos theta by 2, 0, 0 k. 0 and 1 are the two basis states of the vector space, right? Which means that any vector, okay, can be decomposed in terms of these two vectors, 0 and 1. Okay, and that's why it's called a basis state of the single qubit system. Okay. Right, and now we tell that what are the gates now. Okay, gates are nothing but the transformations which change this qubit state. Okay, single qubit gates are those transformations which changes this qubit state, right? And the very common transformations are NOT gate, okay, which actually is a sort of pi rotation across the that means the pi rotation on the z, which means that either it moves to 0 to 1 or 1 to 0, right? Or a Hadamard gate, which takes 0 to the positive axis of x and 1 to the negative axis of x, right? And there are several these type of gates we can so when we looked into this particular gate, actually this was pretty early work when I did in Princeton this particular activity. So we found that depending on the technology, depending on the specific technology, these rotation gates are available. Though ideally we can move a vector very arbitrarily across the at any point on the Bloch sphere, we can move around and play around ideally. But when you look into the specific technology, okay, right, the specific technology, due to the control which is associated with the technology, because ultimately this is your wish of moving a qubit state, right, will be transferred to the qubit system from your instruction to the controller and controller to the physical state of the qubit, right? And these transformation in many of the technology doesn't allows your all own choice. Okay, these are limited by some multiples of some factors of some angles. Okay, so we found that pi by 4, multiples of pi by 4 is the most common choice of the movement, what is found in most technology. But having said so, technology can come up, okay, which can give you more precise. Because why? Because if you have a more precise movement, then what can happen? You can get to your data point more precisely. Okay, so the accuracy of a quantum of a qubit, if you just focus on a single qubit system, depends how fine you can actually update the qubit state. Okay, more fine you can update, you can map your real data to a qubit state very appropriately, right? And if your qubit state are only some disjoint states, and you have a large amount of data, right? That means you might not able to do the 2 to the power n. Okay, fine. And some 2 to the power n states will be noisy states. Okay, so that is the limitation. That means how you can connect with the understanding of the single qubit system to the noise which actually happens in a quantum system at a large scale. Okay. Okay. Another important thing is that when we look into these transformations of the quantum system, okay, this can be mathematically modeled as the matrix operations, right? And these matrices are special matrices called unitary matrices. Okay, so unitary matrices are nothing, the matrices which have the discriminant 1, right? This one property. And a second property is that they will have always an inverse. Okay, so having this inverse makes these quantum operations reversible. Because you have a unitary operation, which is U, right? Which acts on a quantum state psi and generates psi dash. Right? Given you know U, you can always generate U inverse, okay, which is nothing but the conjugate transpose of U. So now if we apply U inverse on psi dash, which you generated earlier, right, the actual operation is U inverse psi, which is I psi, which means you get back psi once again. Okay, so this is the speciality of a quantum system, that you cannot always unroll and uncompute. Okay, right? Unitary gate operation, provided that the unitary gate operation you are doing and applying are perfect. Okay, if there is a difference between what you have, that means you have tried to do and what you have actually happened, then there will be a difference in the vector. Okay, so you can also understand what is error now. So error means you have tried to position psi with a particular value of theta and phi. Okay, but due to local interactions, the theta and phi have changed. Okay, so you targeted to generate a state psi. Okay, but it will generate a state psi dash, which has a little bit cosine difference between the two vectors. Okay, right? And this cosine difference gets increased when we have more and more qubits, because the local interactions increases, right? And these are the challenges, right? I'm not getting you scared that, okay, that means okay, we cannot, but okay, but these are the things. If we understand, then we can build the quantum system in a more efficient way. If we just ignore all these things, we see that everything which is mathematical gets into my quantum system, you will find that what you are actually doing logically and what you are getting in the physical systems are pretty wide. Okay, fine. So I'm not getting into more details. So these are the parameterized forms of all the single qubit operations, and these parameterized forms are very well used in the present day quantum algorithms. Okay, because these parameters are just like weights of the neural networks. Okay, we adjust the quantum parameters of your gates, right? And you try to bring a quantum state, or try to make your quantum state measured at a particular value. Okay. Okay, so this I show a little bit thing that obviously that means another aspect of quantum is obviously one thing is that you do a state transformation. Another aspect of quantum is measurement. Okay, so the same vector can be measured across different axes. Okay, x-axis, y-axis, z-axis. Though mostly in algorithms we exploit the z and x measure. Y measure it's hardly used, though y rotations are used to change the vector, but y measure is hardly used in actual algorithms. Most of the algorithms uses the z and the x measure. So you see that the same vector can have a different measurement on the x and the z, or if we take y. Okay, so this is also a beauty of quantum system, that it is not only the vector you have to know, right? You have to know that on what axis you have to measure the vector. Okay, right? And this is again used very well in the quantum cryptography. Okay, where we try to hide the quantum information by randomly changing the basis of measurement. Okay, yeah. Okay, so now I show two very fundamental issues of the quantum state, but now I generalize it into multi-qubit quantum state. So from a single qubit quantum state space, if we go into multi-qubit quantum state space, it is nothing but the tensor product of all these vectors. Okay, so a single qubit vector is there. We know I can decompose it into alpha 0 and beta 1. Find maybe the first qubit is alpha 1 0 plus beta 1 1. Second qubit is alpha 2 0 plus beta 2 1, and like that we can go on and on, right? And ultimately we can generate a space or a particular vector which is a tensor of all these vectors. Okay, right? And this is very interesting because what we see is that when we use n qubits, okay, we can generate a space which consists of 2 to the power n basis states. Okay, and that is what is being expressed as the first equation. So in the first equation, you see that all the states are of n bits, that all the states are of n qubits. Okay, and the coefficients are 0 to 2 to the power n minus 1. So which means there are 2 to the power n coefficients and 2 to the power n basis states, right? Okay, we have 2 to the power n amplitudes corresponding to each basis states. So which means that we will come back to this when we encode the data. So when we encode the data, we use this property, right? And this is well utilized. Either you say QFT. If you look into the QFT, you will see how an n square algorithm becomes an n log n algorithm. Okay, by this encoding, and we also use this encoding when we try to apply machine learning or okay, we encode it. Okay. Now, when we look into this superposed or multi-qubit quantum states, there are two types of multi-qubit quantum states. Okay, one is bipartite multi-qubit quantum states, which means that this multi-qubit quantum state can be easily generated by independent single qubit quantum states. These are called bipartite quantum states, which means that I can easily identify that this particular multi-qubit quantum states has been generated by the tensor operation of each independent qubit states. Like we show the second example, right? I show the second example is a 2 qubit quantum state because it has 0 0 0 1 1 0 1 1 all the bases, right? And this particular 2 qubit quantum states can be easily decomposed into 2 disjoint qubit states, which means that it's a bipartite operation. Okay, we can easily identify. So what we can do, we can generate a particular distribution over our basis states, and we can find these are contribution coming from individual qubit distributions. Very well, we can do it. But there are some multi-qubit states, for the last example I show, which are called entangled qubit states. Now, these are non-bipartite states, means that these entangled states, you cannot separate out into 2 independent or more, that means, or it's a multi-qubit entanglement. You cannot decompose into, separate it out into individual qubit states. Okay, because as you find that this particular state, which is 1 by root 2 0 0, right, and 1 by root 2 1 1, right, if you try to assume that, okay, there are 2 single qubit states having A, B, and C, D as their coefficients for 0 and 1, you will not able to solve this. You will not able to get A, B, C, and D. Okay, so this is what is called, which we will use later in algorithms and machine learning. These are called disruptive distributions. Okay, which only quantum phenomenon can generate. Okay, no classical phenomenon can generate this type of distributions. Okay, I will come to this later once again. Okay, but now I come to the basic things what we have in our hand, right? If we look into the classical computer, right, the basic systems are the bits which are encoded or which are being assumed as 0 and 1. Okay, right, and there are functional logical gates. Okay, right, in a quantum computer, we have obviously states like 0 and 1, but what I show here is a particular state which is on the surface, right, and which is not aligned to 0 completely or not aligned to 1 completely. Okay, which means that if I project the vector, it will have some proportion to 0 and some proportion to 1, right, and that is what is a qubit, right? And to update a qubit, okay, we have two types of operations. One of the single qubit operations, which rotates this qubit across the x, y, or z axis, called as Pauli gates Rx, Ry, and Rz. Okay, but there are there are two qubit operations which are interaction operations. Okay, which are entangled operations, which can be either XX, YY, and ZZ operations. Okay, so these are the basic tools what we have. Okay, to transform a quantum system. Okay, now when we go forward, okay, let us okay, little bit more insight I will give in the gate operation. So so rotation gate is some now. These rotations are, as I said, across X, Y, and Z, right, are called Rx, Ry, and Rz. And the parameterized thing is that the the theta what you try to rotate, right? This becomes this makes the gate parameterized. Okay, yeah. So now I come to the distribution part. Now distribution is very important because we are ultimately targeting to machine learning. Okay, that means so. Okay, so quantum system or a qubit system, okay, can generate a distribution of a 2 to the power n basis states. An n qubit quantum system can generate a base distribution over 2 to the power n base. Like a single qubit quantum system can generate a distribution over 2 states. Okay, so an n qubit quantum system can generate a distribution over 2 to the power n basis. So if we have to interpret or if we have to absorb a distribution, we require log n qubits. Okay, a distribution having a population of capital N, okay, sample size of capital N, will require a log n size of qubits to absorb the distribution. Okay, to absorb the distribution means that whether I can replicate the distribution, whether I can replicate the distribution of the samples, what is there in my domain, right, in my quantum system, and if I can replicate. So what is the training? Training means that if you try to understand the machine learning in a very very abstract way, training means that I give you a distribution and whether you can replicate the distribution. Same input I give, whether you can also generate the same distribution of the label data, right? I give you a distribution of label data, whether you can generate the same distribution. Okay, so which means that my knowledge is nothing but some way my model is absorbing the distribution and trying to replicate the same distribution. So now what I will show you today is that in the machine learning, and a little bit introduction here, that quantum circuits, okay, that have the power to actually generate distributions at will. Okay, we can generate, that means completely unbiased distribution. We can generate biased distribution. We can generate skewed distributions, all the forms. It depends that how well you mix the single qubit rotation operations with the entangled operations, and can do that means play over the distribution. Obviously, it's not so easy, because when we handle more and more qubits we handle, okay, more and more gate operations comes, and more, that means your tensor operations becomes enlarged, because tensor operations are 2 to the power n. Okay, that you have to compute 2 to the power n. Okay, tensor operations. So okay, but what I can tell you is that if real quantum machines are there, okay, you can obviously do it in a much better way. That noise-free quantum machines are there, right? You can do it at your own ease, right? And that we will discuss. So this is a thing what I show, that this is a very unbiased distribution. Okay, now this distribution can be biased, little bit, right? If we, instead of starting from the 0 position of the vector, if we start the vector itself from some particular shifted position on the state space, and on that, if we apply the same rotation, right, it will be a sort of not this equal distribution of 0 and 1. Okay, so I just try to demonstrate you that how you can. Okay, what you require? That means you tell me that I require distribution 70 and 30. I require distribution 80 and 10 or 45, 35. Probably theoretically, I can prepare the circuit. But okay, yeah, that's the yeah. So now it's understanding this qubit and how we can play with qubits. Now I will go into a little bit higher level abstraction called quantum computing, how we can absorb these qubits, right? And we can build a system, okay, which can compute at large scale. Okay. So from the qubits to the gate transformations, what we try to look forward is a quantum circuits, which is nothing but a sequence of operations on the qubit states. Okay, so this is a figure from the Cascade, which is an IBM simulator. Okay, right on the extreme left, what we show is obviously a sequence of qubits, Q0, Q1, Q2. Okay, one qubit is actually with an unknown quantum state psi, right? And the two other qubits are initialized with a known state 0. Okay, whatever is there. I'm not explaining the circuit, but I'm just trying to say what is being represented here. Okay, right? And then we have a sequence of operations: Hadamard gate control, 2-qubit control, C-NOT gates, Hadamard gates, right? And then we do a measurement. Okay, what is a measurement? Measurement actually, that means actually tries to see. So measurement will be always across a basis. Okay, in the quantum state. So we try to sample the distribution across the basis, and that's the measurement. Okay, fine. So when we try to sample the distribution across the basis, we get different values of different basis states, right? And if that distribution of basis states is what you require, then you have done the circuit. Okay, so we do the measurement and try to get this data, right, and we store it in classical. The only thing what we have to understand here is that those who have a background in VLSI circuits, for VLSI logic, okay, right, when we define a classical computing logic circuit, okay, right, this axis of X is basically space, okay, which means that we start with the input register, then the signal flows to the particular block where the gate works, and then the gate generates an output, right, which is stored in output register, which means that this particular x-axis is space. Okay, here this particular x-axis is time. It is the same qubit register which is acted upon by the different gates, single qubit gates, 2-qubit gates, over different intervals of time. Okay, so the first gate in the left means it comes at the first interval in time. Second gate means it's the second interval, third interval. So it's actually we start with the same qubit state, and we end with the same. Sorry, we start with the same qubit register, and we end with the same qubit register. What changes in computing is the data, right, or the distribution what the qubit generates. Initially, we start with a particular distribution, maybe a very very unbiased distribution. Okay, an n qubit as a register can generate an initially unbiased to the power n basis distribution. With this quantum transformation on time, evolution on time, right, we generate a sort of distribution what the algorithm requires so that the measurement can get the result out of my quantum system. So it means that the computer architecture, what we studied classically, like Harvard, von Neumann Harvard architecture, where we take the data from the memory, comes to the data path, meets the ALU, right, and the logic works and updates, and then again goes to the temporary register, and then either writes a register or goes back to the memory. And this entire computing cycle is different. In the case of qubit system, it is basically very, very sort of in-memory computing. That means in the memory, in the qubit register itself, the data is initialized, and this qubit register goes on update, right? And we are trying to generate a target distribution of the same qubit register, which my quantum gate sequence or quantum circuit will generate. Okay, so my algorithm will be in the quantum system. An algorithm will be trying to define a distribution, what is required in the ultimately after the end of the computation, right? And the measurement of this particular distribution will solve the problem. Okay, so the algorithm development thought process also, you have to just take this thought process and you have to build your algorithm, because the computing system itself is different than the classical computing system. Okay. Yeah, so now I go a lot of things, but you don't need to go into that. Means you can take your time to go through these detailed things. So okay, so this is okay, what is a classical computing system? Because we still believe that the initialization and the first phase, pre-process and post-process, will be still done by a classical computing or an HPC type of system, which will have a quantum accelerator, right, which will implement the stacks, okay, through the various layers. Okay, there will be the quantum compilers, quantum error correction tool chain. There will be some sort of functional modules, quantum error correction. Ultimately, it will hit the qubit, which will be at the lowest level, right? And then there will be control, okay, which will be directing the qubit state transformation according to the program. Okay, so there will be several states, so we can have a sort of quantum quantum algorithm. At the top layer, we need to work. Then comes quantum programming. Okay, convert the algorithm to some sort of execution flow, right? Then you try to, that means look into the quantum architecture. What are the gate resources available? What are the error correction resources available? What are the modules available? Then go to the macro architecture, which goes further and becomes close to the qubit level, where you are trying to also generate the control sequence, right? And ultimately, this is it. Okay, so ultimately it goes to the technology building blocks, which actually hits the qubit system physically, right? And then you can do a readout, right, from the physical system. And then you can again interpret that readout. Because this path, you see, the get result is shortened path, but you have to take a measurement and interpret the measurement as a sort of result which your classical process can accept. Okay, so there is a forward flow and there's a backward flow. Okay, right, which actually defines the interface of the quantum and the classical system. Okay, right, and a lot of things are there. We have just, and this is a very good paper. You can look into this 2013 paper on ACM. Okay, which has given a sort of blueprint of a quantum computer. Okay. And now, if we look into the quantum algorithms, okay, right, okay, this is the work what I started actually. That means this I got exposed when I was again in Princeton. Okay, so we took some of this, so in Princeton and the collaboration group, what we have around 10 top universities in US. What we tried to do, we tried to look into the algorithms and try to estimate the resource of the quantum. So we had that over the years. When I was in Princeton, the number of algorithms were around 100 or something, 100 plus, right? Over the last 10 plus years, right, it has increased to double. Okay, 300. Okay, 300, almost 300 algorithms we have now. Okay, 300 plus algorithms. Okay, we have. So okay, so these quantum algorithms okay have lot of, that means okay, they can be classified into a lot of forms. Okay, some are search algorithms. Okay, the good point is that means quantum search is very strong, right? And why quantum algorithm can work good in optimization? Because an optimization problem is basically a search problem, right? You are exploring the parametric space so that the right choice of parameter can minimize or maximize the function. Okay, so basically you are trying to search the parametric space of a function, okay, and trying to find the best values which can give your cost bound. Okay, which satisfy your cost bound. Okay, so but obviously there are various applications of the quantum. Some are solving some algebraic problems. Okay, some are solving some combinatorial problems. Okay, graph problems like this. Okay, some are working on search. Okay, search optimization, right? And now machine learning will also come up. So it's always good to actually, but the main thing is that if we try to think very focusedly, that if I try to solve an algorithm, right, we need to know that what are the transformations we need to apply on the qubit state, right? Okay, right? And these quantum transformations should be doable in the quantum technology. Okay, this is the thing. So if it has to be doable, right, we have to interpret our quantum technology in terms of some sort of universal quantum gates. Like we have universal logic, right? Any function we give me, right, any arithmetic and logical function you give, fine, right, universal logic gates can implement that. Okay, so if we can have the universal set of quantum operations, okay, there, then probably this is fine. Okay, but this exploration is okay. That means I think it's still there. A lot of things has been closed and defined, but I think it's still there. That what is the best set of universal quantum gates, okay, which we will use, okay, so that that means a large number of quantum applications can be supported, and that you need to only, because when you try to build your quantum hardware, see why ALU design is so strong. Still the classical computers, because in ALU design, we have understood that what are the fundamental arithmetic and logical operations needed to actually make any algorithm work, any application work. Okay. And now this is, I think, still a challenge in quantum, because first of all, different technologies supports different type of primitive, which says a quantum primitive operation, right? And this quantum primitive operation, either single or multiple quantum primitive operations will define a high level quantum universal logic operation. Okay, so now universal quantum logic operation will define that, okay, this is sufficient. Okay, to have these quantum primitive operations in my technology is sufficient, because I have defined the universal quantum logic operation, which will be mapping my high level function to the quantum technology seamlessly, right? And this is still a little bit variability is there. Okay, fine. Now comes the quantum programming. Quantum programming, that means obviously, that means we know that a type of that when we try to execute our particular application on an hardware, okay, right, we have to that means have certain sort of languages, right? And there are standard languages which are okay, something called this QSIM. I think the C-DAC team has developed. Okay, right. Qiskit is there. I think we developed something called Chasm. There are a lot of high level flows are there, right? A lot of high level flows are there, but ultimately, all these high level flows will be mapped into the low level quantum operations. Okay, and then these low level quantum operations will be mapped to quantum control, because corresponding to one low level operation, maybe you need to generate 3 control signals or 4 control signals or 5 control signals. You don't know, right? It is obviously a technology which I am also not very okay. That means yeah, I'm a knowledgeable person in that domain. Okay, so this mapping will exactly give you the quantum cost. Okay, because quantum cost is also something which you have to compare, because whenever you have large scale quantum system, people will raise a question that what is the need of large scale quantum system? Okay, can we not do it in classical computing? Okay, so you know that Scott Aronson, when I was in my mid of my PhD, I visited Sunny Buffalo as a visiting scientist, right? And then at that point of time, 2004, 2005, okay, Scott Aronson was a very strong, what I can say, he was okay, he was saying that, that most of the quantum algorithms have a lot of post-processing and pre-processing, fine, which actually doesn't doesn't takes this quantum supremacy, right? What we say is only the quantum part. What we have to do long chain front and back, okay, to support this quantum supremacy, which again comes to the a similar cost. Okay, so he was a quantum skeptic initially, but now I think Scott Hansen is also very much for the quantum, right? He is working very strongly in the quantum algorithm. So so these are the things which we need to understand, that it is not that I have successfully developed a quantum program. It's a chain which you have to successfully complete, okay, with multiple okay, team of experts, and we can do it. Okay. Yeah. So the other part is that in order to, that means I think some of you know my background is EDA. Okay, I basically started my career from ORCAD, which is now in Cadence, then shifted to academia and research. But I am always a loving, that means always a person who loves EDA. So okay, so design automation is a thing which actually okay, that means exploits a design and bring it closer to the technology. Okay. Similarly, now quantum EDA is also available. I think Keysight, which is there, I think they are providing good tools. Okay, where you can actually so a design is very high level, right? And if you have to close the design, right, you have to understand what are the metrics in which the design has done well and what are the metrics the design hasn't done well. Because the metrics for the design hasn't done well, you need to improve on that and need to make a better design. Okay, so those design analysis can only be done if there is a EDA platform. So there's a good EDA platform. I find it out. Maybe there are some other EDA platform also there, which is offered by this Keysight. Okay. Now I close in the quantum computing part now on telling that, okay, this is the flow. Okay, this is a generic flow, right? Okay, so we have a problem definition, you generate a quantum algorithm, generate a quantum circuit, verify the quantum circuit using a compiler, okay, right? Try to, right? And then the compiler can be for two forms, okay? One is for a real QPU, physical QPU, which are obviously still very less, okay, or a quantum simulator like what NVIDIA provides, Pennylen provides, okay? Okay, right, which are basically accelerated simulations. Okay, they have the that means if we just try to do a normal vector multiplier type of backend, right, it will not work because it will saturate after a few size of the qubits. Okay, so you require some sort of special techniques like compression of these descriptions, right, and these matrices you have to okay, they are sparse matrices. You exploit the sparsity techniques, and you have to do something on that, right? So okay, so quantum simulator, yeah. As my research group has also developed a simulator. Hope it will be coming in IEEE software systems pretty soon. It's called a C-DAC. It has been published in a couple of places. Okay, that means it now goes up to 50 qubits. Okay, 30 qubit was there, now goes to 50 qubit, which is a joint work with Nanyang Technology University. And we have not only simulating the binary quantum circuits, okay, but the multivariate quantum logic can also be simulated on that particular thing. Okay. Once it is out, I will connect all of you to that. Okay. So, okay, so that means after this part ends, I will try to. Okay, how much time I have? Any? Oh, good. That means all have to be there with me. Okay. Okay, fine. So now what I will try to discuss a little bit of this quantum algorithm, just to see that how we can take this take this idea of qubits and quantum gates to some of the very basic quantum algorithms. Because before I push you to quantum machine learning, which is a little bit a lifted thinking, I thought that we should have some sort of fundamental discussions on quantum algorithms to get a taste of it. Okay, so this is okay. That means in order to understand the quantum function, okay, this particular understanding of this particular toy example, I will say, toy example is very, very important. So anybody can figure out. That means I will now go a little bit interactive way also to keep me a bit relaxed. Okay, so can anyone help me that what is this particular thing going on here? So So I will tell what I have shown here. I have shown an input register, which is a 3-qubit quantum register, which is in full superposition. Okay, right? And so it can store 8 basis states. So the 3-qubit register is now holding a data space which is defined in terms of 8 basis states, right? Each of the states have an amplitude. Then I pass it to a quantum function, which is a black box, right? And then this black box changes the register. That means though I have written input and output register, it is not the physical input output. It is the output state of the register, right? And the initially was the input state of the register. It's not a physically two different registers. It's the same register. Okay, as first we initialize and then we pass it to, then we do a quantum operation, right? And then we come to the output state of the register. Fine. What has happened? Can you tell? What has happened of this? What happened due to the application of the function? Two things happened. If anyone can help me.
The amplitude has changed.
Yeah. So the distribution has changed. The distribution of 0, 0 to 1, 1, which was there. Okay. Their coefficients have changed. So the distribution is a little bit different now. And another thing is that the function has worked over all the basis state simultaneously. Okay. So you operate on the 3-qubit. You take that means obviously you have to define a 3-qubit function, obviously. Okay. So a 3-qubit function. Suppose you have an hypothetical 3-qubit function. So a hypothetical 3-qubit function works on the 8 states, 8 basis states simultaneously, right? And this particular function can be made an oracle function. I will come to later when I go to the Grover search. Okay. So oracle function is something, okay, which actually for our particular states, that means it generates a very different outcome. Okay, corresponding to the other states. So oracle is a query function. So okay, suppose a very simplest query is that for some input it generates yes. Maybe to make it further simple, for one input it generates yes, and for all other inputs it generates no. Okay, it may be a simple oracle function. So in that case, this function will actually make the amplitude of the particular state for which it has generated yes very different from the amplitudes for all other states which resulted no. And this is called marking of the state. If you look into many of the quantum algorithms, you will see that that means the oracle is used and the quantum and the state is marked. Okay, but here I didn't show anything, any marking. It's a very generic way of description. Okay, so good point. What I think one of the participants identified is that it changed the amplitude. So this change of amplitude, because though the function is applied parallelly, but function is working independently on each of the states concurrently. And depending on the state on which it is acting, it is generating a sort of transformation, right? And so that transformation is resulting to a different distribution. Okay, that means in the output state of the register, of the qubit register. Output statements after the function has operated, the state of register is the output state. Okay, so the output state of the register. So and this functional parallelism means that we are actually doing exponential computing. Okay, because we are actually a 3-qubit, right? A 3-qubit function can operate on 8 states. A 4-qubit function can simultaneously operate on 16 states. Okay, so the computing power is here exponential to the size of the function. Okay, though the question is at all that can we make a 4-qubit function? Can we make a 6-qubit function? Yeah, the answer is no. We have to decompose a 4-qubit function to a single qubit and a 2-qubit function, because the decomposition technique, this I'm not touching here. Okay, this decomposition technique was entirely my PhD work. Okay, it's called quantum logic synthesis or quantum circuit synthesis, where we designed a lot of mathematical techniques to actually decompose a certain quantum function to some implementable quantum operations, because ultimately that means as far the present technology goes, the implementable quantum functions are single qubit and 2 qubit. So ultimately you can have a very high level description of a quantum logic block or a large quantum oracle, but ultimately to implement that, right, you have to decompose it, you have to synthesize it. Synthesis means you have to make a larger box using smaller components. The synthesis, okay? So ultimately the larger function of large qubit size will be ultimately synthesized in terms of single qubit and 2 qubit functions. But that I am not covering here. This is the functional form. But if you tell that, sir, how we will actually map it to a quantum hardware, then you require the synthesis. Synthesize this function into single qubit and 2 qubit operations, and then you map it directly to the single qubit and 2 qubit operations what you have in the particular technology or in the particular QPU. Okay.
The synthesis is at a software level.
Synthesis will be done by the compiler, but the knowledge will be taken from technology. You need to have the technology input properly, because there is a cost associated to synthesis. So there is a trade-off in quantum. Okay, the difficulty part is that you may not accurately synthesis. Why I'm telling? If you try to accurately synthesis, you need to make a very long chain of gates. And this long chain of gates increases your qubit depth. So now you have to make that means, and if you try to restrict it, it's called Solvay-Kitaev decomposition, and there are other decomposition techniques are also there. Okay, that means what you need to do, you need to give an error threshold. Okay, so now if we make the error very, very, that means if your error threshold is very, very small, then you are decomposing into the larger gates, which requires more synthesis time and which increases the qubit depth also. It's get depth. Sorry, not qubit depth. Sorry, get depth. Okay, get depth. Right, and if you try to make the error threshold a little bit higher, then obviously your get depth is saved, right? Synthesis time is saved, okay, but error is more. Okay, so you have to make a trade-off of what is the error you need to you can absorb in a given algorithm. Okay, suppose for distinguishing between an apple and an orange might not be, you don't require such a strong classifier. Okay, but maybe when you are trying to distinguish between different varieties of orange, okay, then your classifier, then your feature space becomes much larger. Okay, and then you might have to take decisions very accurately, because your classes may be very close to each other in the feature space. Okay, so those are the things. Obviously, that means in some cases you can have the cost taken absorbed, but some cases you don't need to do that. Okay, fine. So now I go to a very, very fundamental algorithm by which we start the quantum algorithm course. Okay, which is called a Deutsch. It's called a Deutsch function, or a Deutsch algorithm. Okay, so the algorithm is pretty simple. You don't ask me that, sir, why do we use it? You can use it some query problem, but this is a very simple problem where given a string of bits, okay, which are encoded in 0 and 1, right? You have to tell that okay, the function is balanced, right, or it is not, or constant. Okay, function is balanced means for half of the inputs it gives 0. Okay, so the function output is either 0 and 1. This is the constraint. Okay, this is one of the logic. Okay, so you give me an n bit of input, but the function only will give 0 or 1, right? And if it gives 0 all the times or 1 all the times, it's called a constant function, right? If it gives a 0 of the half of the times and 1 half of the times, it gives a balanced function. Okay, so now in the classical case, I think you need to do at least of the order of, okay, that of the order of n. In that means n by 2 or some observations or some that means n by 2 at least you need to do. N by 2 call of this function you need to do to tell that whether the function is a balanced or constant. Because if you just cross n by 2 and see that, okay, it is giving the same value, it's a constant. Okay, if you just cross n by 2 and if you get that okay, there is a difference, then you say it's a balance, something like that. Okay. Yeah. So yeah. So now a particular function. So what I show here, this is a very simple that is simple functional form of a quantum circuit. Okay, in terms of algorithm, what this circuit tells. The circuit goes through a unitary transformation. How we will achieve the unitary transformation, that is a different way. You can show a preliminary form of this function using a C-DAC gate also. Though it is not a single C-DAC gate only, right? But a C-DAC gate, if you see, a C-DAC gate is a control NOT operation which actually flips the control qubit depending on the flips the target qubit depending on the control is 1 or 0. So, okay, so the value of the control qubit, okay, and the value of your target qubit are accepted, right? And accordingly, it does a sort of operation which is XOR the Y XOR X, where this X can be defined as a fx, okay, Y XOR fx. So basically, you can design these unitary operators, can design these functions which are using the C-DAC and some other gates, can design a function where Y XOR fx. Okay, in the case of simplest C-DAC gate is Y XOR X. But you can also design a function something like Y XOR fx using this quantum circuits, unitary circuits. Okay. Okay, now Deutsch algorithm setup is something like this. So as I said, that we have to evaluate the function. So okay, so in the case of a single say say a single 1-bit function, okay, that a function can only have, that means a 0 input or 1 input. In the case of a single bit function also, single bit input function also, classically you have to evaluate twice. First, you have to pass 0 and see what is the output. Second, you have to pass 1, you have to see the output. If you see that both the outputs are same, then it's a constant. If both the outputs are different, then it's balanced. Okay, so you have to evaluate at least 2. Okay, so Deutsch, this is very, very historic, so I'm discussing. It's not that how we will use it, okay? It's more historic. So the historic point is that Deutsch shows that in the quantum, you need to only call this once, right? And this was his mathematical part of this stuff, okay? Okay, what it did, he actually, that means actually the upper part is your input, okay, which can be 0 or 1, whatever, right? And the lower bit is a sort of ancilla. The second bit of the second qubit of the register is an ancilla. Okay, both actually, okay, transform to H, right? And then this black box actually evaluates X and Y XOR fx. Okay, he showed that you operate once this function and you use an Hadamard gate on the top, on the first qubit, and measure it, right? You will know that what is this function, right? And the entire mathematical flow is given here. So initially, what is psi1? Psi1 is Hadamard of 0, which is 0 plus 1 by root 2, right? Hadamard of 1, which is 0 minus 1 by root 2. If we expand the state, it becomes the entire psi1 before the input of this particular gate is this state. Okay. Then what is done? Then you do this operation, Y XOR fx. Okay. So when we do this operation Y XOR fx, right? If it is constant, fx can be always be 0. Okay. If it is constant, it can be constant 0. It can be constant 1. So it can be fx can be 0, fx can be 1, right? And if it is balanced, it can be x or it can be x XOR 1. Okay. So if we try to take out all the possibilities what psi2 have, you can cluster it into two possibilities. Okay, f0 equals to f1, which means it is a constant. Okay, then psi2 has two possibilities. Okay, right? And if f0 not equals to f1, which is means the balanced, then it has also two possibilities. Okay, but the unique condition is that in both of the possibilities, the first qubit is different. If f0 equals to 1, the first qubit is a superposition of 0 plus 1. And in the second instance, the superposition of the first qubit is 0 minus 1. So now if we hammered on the first qubit, right, and if we hammered 0 plus 1, we get 0. And if we hammered on 0 minus 1, we get 1. So in the first qubit, if we measure 0, it is a constant function. And in the first qubit, if I get 1, it's a balanced function. So that exactly was the Deutsch algorithm, right? I'm not getting into further. This is exactly the Deutsch algorithm. If it is 0, it's constant. If it's 1, it's balanced, okay? Then what it's done, okay, so classically we require this amount of time, 2 to the power n plus 2 plus 1. So now Joyce, I was very lucky to meet Joyce in Cambridge when I was a visiting professor in 2018. He's from Sri Lanka. He's a professor, emeritus professor, Department of Mathematics at Cambridge. Okay, a very phenomenal professor, a very down-to-earth, humble professor. We had a good meeting, or that means around an hour with him. Okay, so Deutsch. So Joyce worked with Deutsch, right, and extended the problem for a string of n qubits, which is obviously of some importance. If we can explore, because this gives us some sort of feature of an n qubit data, right? Some sort of feature of an n qubit data, and this can be done. So for the n qubit, the particular classically we require 2 to the power n by 2 plus 1 operations to actually find out whether it is a balanced or not. Okay, but similarly, Joyce does only with a single oracle call. So Joyce became so interesting for this. Why it is so interesting? Okay, let's see what it is. It's the same thing. It's exactly the same thing. Like nothing more. Only the thing that he actually expanded the function to an n bit sequence, n qubit sequence, which means over 2 to the power n basis. Okay, and exactly the same thing is being done. You can just look into this, right? All this phase. Only the thing is that when we try to do XOR is equivalent to -1 to the power fx. Okay, the XOR, if we try to expand this functionally, okay, it becomes -1 to the power fx, and that played a very big role, right? And then it is actually, if you do a Hadamard, it becomes -1 x2 dot z, right? And this measurement resulted that what is the actual value, constant or balance. So if we see that in the case where the function is constant, the coefficient of this 2n is equal to plus or -1, that is, it has an amplitude of 1. Okay, in the case the function is balanced, okay, this will be 0, right? And so it will measure 0. So again the same measurement 1 and 0 will tell you that what effectively is the n qubit feature. Okay, and this probably can be taken for a quantum communication channel. Okay, where that means that's a Bob and Alice. Okay, so the Bob and Alice are separated. Right? Alice is trying to determine whether the function is constant or balanced. Okay, so what I do is that means you throw me. So Alice in classically. Okay, in classically Alice has to Alice transmits 2 to the power n plus 2 messages, each of size n bits, and tries to see the blob's reply, right, and get what it is, this function. Okay, but quantum mechanically, Joyce, right, it can just send an n plus 1 qubit, because 1 qubit is required for the ancilla. Okay, right, to which Bob replies with the n qubit message, right, n qubit measurement, whether all 0 and all 1. Okay, right, and that tells that what is the function. Okay, this type of this is again a sort of thought application, but this can be exploited, right? People did that. Okay, so the next killer application on the Grover, on the algorithm side, obviously there are So many killer applications. I'm not discussing all of them, but these are two fundamentals. The Grover search algorithm, right? And why this is very important is that, as I said, that many of the computing problems can be mapped to an optimization problem or a search problem. And actually, optimization problem can also be a search problem in a hyperspace. Okay, the optimization problem is basically a search problem in a hyperspace. Okay, but again, this is a very toy example. Okay, what is a toy example? The toy example is that suppose, okay, that means the law of Grover's point was that means to search an unsorted database, right, and to find that whether the key is present in that or not. Okay, so to search an unsorted database, okay, that means in the classically you need to do at least n calls. Okay, so there is a oracle, okay, which will accept the data, right? And if the oracle, that is oracle condition matches with the data, then oracle will give yes, right? If the oracle condition doesn't matches the data, okay, the oracle will give no. Okay, so classically, if we have to search a list of n which is not unordered, we have to call, in the worst case, we have to call n operations, n, and in the okay, say average case, you have to do n by 2 calls of the oracle. Okay, now what quantum does? In a quantum, the entire data can be superposed and can be passed to the oracle O1 time, because we have already seen the functional parallelism in the toy example, right? So what I do, I actually generate the entire data space as superposition of log n qubits. Okay, if there are n elements in my data, in my unsorted list, so I use log n qubits, right, and generate n data elements in the unsorted database, and I pass the entire thing as superposed state. Okay, the oracle will also generate a superposed outcome. Okay, fine. Out of this one will be yes and rest all will be no. But now, can we measure here? This is a question to all of you. Can we measure at this point of time? So you have got an yes. If I measure the qubit register, whether I will get it. Probability is 1 by root over 2 to the power n probability of getting it, because each are now equal. Each are all equally, though I have marked it yes, but equally. It is all equally probable. So I show this in the terms of distribution in the lower diagram, where I show initially it was the extreme left. All was on the same probability. Then this yes, and this is the oracle trick. Oracle will be made such a way that once the condition satisfies, this particular amplitude will be marked, or we will phase inverse the amplitude. So the amplitude of that particular state, which actually maps the oracle true, its phase is inversed, right? And once the phase is inversed, then if we try to measure just here, still also the amplitude are all the same. So the probability is the square of amplitude. So still all probabilities are same. So you don't know where you will fall. But your target is that you need to fall on that particular state which has measured yes for the oracle. So in order to do this, what you have to do amplify the amplitude of this particular state, which is the next part of the Grover. The Grover has 2 steps. One is the oracle call, and another one is the amplitude amplification. So the amplitude amplification is basically of the order of root n. Root n times you have to operate the amplitude amplification. Still you have a quadratic speed up. Okay, we have n or n by 2 corresponding to root n. Still you have a quadratic speed up. So now this amplitude amplification, what it actually does, right? If we try to see it in terms of the distribution, amplitude amplification does a mean first of all, and then subtracts the mean. So what do you do if you take a mean now? Okay, now as 1 is minus, okay, the mean will be little bit less than all of them, right? And if you now subtract this mean with all of them, you will find that the negative amplitude actually increases and the positive amplitude decreases, right? And this is in terms of distribution. Okay, there is also a geometric interpretation of this, which is also, if you find the Grover's paper, I think around 1990, I think this paper was published. Grover's phenomenal paper, right? You should read that paper. Okay, I push this paper to my students in the class, but this is what is actually done. So you see there are two states. One is S dash and one is S. What is S? S is the state vector of the state which has been marked yes by the oracle, right? And S dash is all the other states are in S dash. Now, if we have to apply measurement theory, okay, these two states will be separable completely if they are more and more orthogonal. So you have to make that means you have to make S orthogonal to S dash. More and more you are close to orthogonal, more and more your probability of getting S will be higher. Okay, so what it does in each of the steps, right? It does a reflection. It does a reflection over S dash, right? So first it gets reflection over S dash and comes in the bottom part, right? And then it again gets reflected. So in each reflection, it becomes closer to the orthogonal axis, right? And then at a point, and this is again estimated root. Actually, the exact that the estimation of root n by root n operations comes with this particular this description of geometrical description, right, of the amplitude amplification algorithms. Okay, so with this you will ultimately reach the orthogonal state, right? And now if we try to do the measure, this will be 0 and this will be 1 because these are all oriented to 0, right? And this is oriented towards a 1. Okay, so this you will get. Okay, this is the another theory of trying to understand what happens in the amplitude amplification. One is from the distribution point of view. Another point is a state vector point of view. Okay, so actually when we look into quantum algorithms, both these visualizations can be done. One is a state vector visualization, and one is a distribution visualization in terms of the of the state. Okay. Yeah. So I think I will close maybe by next 10-15 minutes. Is okay. Okay, right. Sorry, I'm keeping you held up, but this I will do a little bit fast. I think we all have understood the basics of how to work with quantum algorithms and what are the key insights of this, right? Okay, so what I now try to say, this is a very well-known, I think, a top figure everyone has seen, right? These are the ways our classical quantum and quantum. So one is the data and one is the quantum. I think presently we are working with classical data and quantum process. Quantum data and classical process is quantum simulation, which is also a very strong part of quantum, that means of our NQM. Right, and quantum data and quantum processing is something called quantum sensing, which is also a very strong part of quantum. Okay, of a national quantum mission. Okay, so what we are trying to do here, actually, quantum chemistry, quantum optimization, quantum whatever it is there, right? We are trying to so the first part of the circuit is basically the way we encode the quantum data to the classical. We have to do an encoding of the quantum data to classical. Second part are the parametric gates, which will transform the quantum states. And then we will measure, right? And hopefully we will get the distribution, what the domain requires, right? And this exact matching. So the difference is a loss function, right? And more we match, more and more we reduce the loss function. Okay. So what I show here is already discussed. But what I show here is that means multiple. This is an example of two qubit state space. 2-qubit state space, very well distributed 2-qubit state space can give a very good distribution, which is all the states are equally probable. Okay, two unbiased coins. Two unbiased coins are represented, but then it becomes a little bit different when I introduce entanglement. And when I introduce entanglement, the different ways I introduce entanglement, I can move from a completely non-entangled state to a little entangled state to a more entangled state and a totally entangled state, which is disruptive distribution. Okay, so this is something we can actually have a very well control on what distribution we want. Okay, in terms of the outcome. So okay, so quantum circuit can actually generate. So if you try to say from here to here, this means all power distributions are there in my control. Theoretically, I'm not telling practically whether in the quantum hardware we can generate all distributions at will, but theoretically I can show that you can generate distributions at will, right? And machine learning is nothing but learning distributions, and you can absorb distributions through your circuit, and basically tuning the circuit for a particular training data means that you are exactly replicating the distribution of the training data, okay, as an outcome of your quantum distribution. Okay, so I'm just skipping a bit, right? And this is how the circuits are being done. I'm again skipping a bit due to the time. So now what I show here is that these were the quantum circuits when I was doing my PhD. It was the fast generation quantum algorithms, which are definite quantum circuit. Like I show the Grover circuit, the Deutsch circuit. Those are definite quantum circuit, right? You know that what are the unitary transforms you need to do. Definite unitary transforms you need to do. Only maybe the size of the transforms will vary, but the number of qubits will vary depending on the size of the problem or instance of the problem. Okay, but now the second generation of quantum algorithms are parameterized quantum circuits. Okay, where we actually focus more on the varying part of the distribution. Okay, because we are learning something. Okay, those were not learning circuits. Here we are learning something, mean we are actually trying to adjust my distribution with the distribution which is given in my, that means in my knowledge abstraction. Okay, so these are the circuits which are QAOA, VQLS, PQC. Okay, so all these circuits are actually fundamentally U theta circuits. Okay, so the parameters of theta are for the single qubit rotation operations and the coupling operations. Okay, so now I will go into a little bit, maybe the next 5 minutes I will just cross that how we will encode the data, right? And so the first part, if you see the first part in a quantum machine learning, right, that or a general quantum algorithm also, if you try to take it completely from classical to quantum, first part is that means the data encoding part. Okay, so this data encoding part is the first part, which is the EX. Then we do the parameterized quantum circuit, which is basically after mapping it to the feature space, I apply a kernel. What is a kernel? Kernel actually tries to sample the distribution in the feature space, tries to maximize certain feature values and try to minimize certain feature values. Okay, so similarly the U theta also does something like that. Okay, so let us see how it works out. Okay, so simple encoding is a basis encoding. Okay, what I show here is that this is your X, which is a k-dimensional vector, means in the concept of feature space of, okay, that means it consists of k independent features, your feature vector. Okay, so each of the feature values are encoded in the binary form. So all are encoded into the B11 to B1n, okay, or BK1 to BKN. Okay, for example, I show a feature vector having two features, 1 and 3. So I expand 1 in binary, I expand 3 in binary, and then I develop the quantum encoding by actually using 4 qubits, which are initialized with 0, 1 and 1, 1. Okay, but this is good. That means This is a good way to do because it's not scalable, right? Right. If we have a large feature values, and if you have a large vectors, right, it is not scalable. You require so many qubits, okay, to handle, right, and you require large gates also, okay, to handle the feature values. So it's not for smaller values. People work with this. Okay, this is what is very comprehensive. Okay, this is actually, that means amplitude of the basis states are, that means are encoding your data. It's called the amplitude encoding. So what I do, I actually have a vector, same thing. The vector having k features. Okay, so I normalize it. The normalization is very simple, like this. What I show here, normalize. So I do the squares of all the values and do a root over, and with that in the denominator I divide each of the values. Okay, so that, because your constraint is, because as you are encoding across the basis, your constant is the sum of the square of the amplitude will be 1. So you have to normalize it. Otherwise, you cannot make that constraint. Okay, so you normalize it, and this you generate like this. Okay, right? And you so what do you generate? You generate a space, superpositions space. Okay, so this is how you can encode a feature space, a larger dimensional feature space using the quantum. Huh? There is also another technique which actually gives you a better in terms of the non-linearity of the feature space, because all those others are basically a linear mapping. If we do this angle encoding, though angle encoding has several forms, this is the most simplest form. Here, for each feature, you actually encode it in terms of a one rotational parameter. Okay, so a qubit is rotated, okay, by twice of normalized value. It has to be normalized value, understand? Okay, x1 to x2 to xk are normalized, and that normalized value goes into 2 into x1 for the ry gate. Okay, it can be rx also, it can be rz also, but normally we take at one, that means at one axis we do it, right? Sometimes we take 3 axes, okay, to encode much larger space, but I'm not showing it here. So so this is the way how you can encode each of the values in the classical domain to an equivalent qubit state. So what is encoding? Encoding means that we have to represent the entire value of your classical data into a qubit system. Okay, because qubit system will be only expanded across the basis amplitude of the basis, or they are parameters in the Bloch sphere, okay, by which you can encode it. Okay, those are the things because ultimately you have to again get back to the classical value. Okay, you have to decode it ultimately. Okay, so this is what are the simplest encoding form. There are also other things. So as I said, that the angle encoding gives you, as there is a non-linearity, because you are doing in terms of this cosine, okay, this type of functions, exponential functions, right? You can actually map a non-linear space to a linear space to the transformation, which is also done kernel trick in many of the classical ML problems. We use a feature transformation, right? In classical, we use a feature transformation by which we take a non-linear space to a linear space by doing a feature transformation. Similarly, we are doing here, and that actually makes some of the problem easier to generate the class boundary. Okay, because the non-linear problem becomes linear due to the transformation in the angular space. Okay, right? And this is what is actually done. So after you have done this data encoding, you have to now give this parameterized U model to map your labels. So your labels have a distribution, right? And that distribution should map to your entire training data. Okay, so you try to that means the way you do neural network, you can have some random random values and then random values of the gates, and then you can try to do this random values of the gates. There are certain well-defined technique which I'm not discussing now, but there are techniques called answers by which you can actually, because you cannot just put a block u theta, because then you cannot control, you cannot actually tell that, okay, that means an u theta, I will control the theta of a 5 qubit or 10 qubit gate, because that will not be a good control. Good control is that if you can vary the smaller, that means the more smaller controls you can have. So you have to decompose your u to some smaller u's, right? And you have to make those parameterized, okay, so that instead of a one single weight controlling the entire network, right, you have weights across the multiple branches of the network so that you can control the network well. Okay, so that decomposition is called an answers decomposition, where there are standard techniques are there by which you can decompose okay, so horizontally, vertically of this. So that is how you can define the component, how you can generate the r theta by decomposing into multiple thetas. Okay, so all those decompositions are there, which are very standard approaches are there. Okay, that means, and these answers might not be unique answers. Okay, but your target should be, that means your answers and maybe my answers, okay, fine, should actually overlap into the maximizing the outcome. Okay, so your answers should be such that means both actually cover the solution space. Okay, right? Otherwise it will be difficult. Otherwise you're out of the solution. So these are some of the things that means, and again, when you design the answers, you have to take the hardware into consideration. Okay, you are doing u theta, but whether those u thetas can be done in the hardware. So you need to have some sort of input from the technology also, okay, in order to do it very precisely. Okay. Okay, the last part is the expectation value. Okay, what is there? So so once we have generated a distribution, okay, the expectation value is that means what you are trying to, what you can get for a particular basis. Okay, so the expectation value of a basis in a given quantum distribution. Okay, and your target is to actually increase one basis or certain basis states compared to the other basis states, right? And whether you have performed well defines that whether the expectation value for the basis states, what you have theoretically tried to achieve, whether that expectation value have been achieved by your circuit. Okay, to do this, you need to actually do this particular thing, which is actually a state psi, right? And there is an the average value results of a quantum operator. So this is a psi bra z, and psi kate, okay, which actually you can take a sort of this fine, this can be a sort of, so if you see a basis state there z, okay, so the basis state of z is a probability of something which is 1.p0 plus minus 1. So this is actually the probability of measured getting 0 or getting 1 in the particular distribution. So this is so this way you can actually try to, so eigenvalue is a value of the basis vector. Okay, so if you do a transformation, okay, that means u on a basis state, right, it will give a sort of eigenvalue and the basis vector. Okay, so what you are trying to measure, that means the eigenvalue for a particular basis state for a given operator. Okay, and that is what is the expectation value, right? And you can do an average of expectation value for all your entire training set, okay, for the different levels, if a classification problem, for the different levels you have, and if that expectation value matches with the training data set, you are fine. Okay, so so these are the ways you can actually try to measure this. Okay, right, I will not discuss much. So these operations can again be taking a classical, so here HPC comes into the play. Okay, because a lot of optimizations you need to do to actually, classical classical soft computing techniques can be applied, or classical optimization techniques can be applied to actually update this theta of the circuits, right, and minimize the loss function. Okay. Okay, so I think in summary, the quantum learning is something like this. Okay, this is the classical learning on the extreme left, right? On middle, I say the quantum learning, where it takes the input space to the encoded Hilbert space into phi x, right? And then this class boundary is basically operating the further the ux theta. Okay, so here there are two components. One is ux, which is the encoding part, and theta is the parameterized quantum circuit. Okay, so both works together and tries to generate a measurement, and this measurement, suppose this measurement operation is basically across the basis. Okay, so you try to measure across the basis, and if we suppose there is a it's a binary classifier. In a binary classifier, you partition the feature space into two partitions. Okay, so you can take one partition as basis 0 and one partition as basis 1. Okay. In the case, the good point is the value saved. The savings is that if you are having an n levels, you can actually use log n qubits, okay, to design your to actually estimate your outcome across capital N levels. So capital N levels required log n qubit space to actually, okay, so distribution is a log n qubit space, though the log n qubit space will distribute an n level data. Okay, so those are the, so now you define the, now you map your measurement for each of the data in your training set to your levels, right? And so expectation value of your basis states will be mapped with the levels corresponding to the training set data, right? And if you can make a higher expectation value for all the data levels, okay, for the corresponding basis, then your training is done. Okay, though there are a lot of okay, plus what I can say, people are well supportive that quantum machine learning will be good in the long run. And again, there are a class of people who are telling that quantum machine learning is very difficult to converge. Okay, so these are the thoughts, but we have to do more experiments, and we have to, that means we have to do more sort of learning on this thing. So I will not go into detail. These are some use cases you can go through, not explaining this. Fine, these are also some of the things you can do in terms of the this modeling. These are the quantum media. These are some of the very good examples of the industrial solutions you can generate. Okay, as in the NQM, we are focusing on a lot of the products what we can develop. That means in the quantum algorithm and application, the group where I am, okay, belonging in the NQM. Okay, so there we are. Okay, there we can target a lot of this. Okay, this is the C-DAC, which is a consortium of quantum technology and application consortium. Lot of okay, top quantum organizations like IBM, NVIDIA, Pennylen, right? All are there in this particular C-DAC consortium. Okay, so they have actually identified some industry, business impact, problem domains. Okay, all these things, and you can go through this, right, and take up. Oh, sorry, and these are some of the things we are doing. Yes, I'm skipping this. And these are my group of the researchers. Okay, most of them have joined industries, right? And a few will going for PhDs of latter, the interns and all this. And yeah, so we have a lot of collaborations. Obviously, C-DAC is also one of our strong collaborators, and yeah, we have a lot of collaborations here. Yeah. So conclusions, what I try to say here is that means obviously quantum optimization, and we are just I think in the very beginning. Okay, lot of things needs to be done, right? Obviously, we require the quantum hardware also to do that. But I think, yeah, that means quantum, that means all the development should actually start. And if we can do that, we can contribute in many of the important applications of science and technology, the material search, okay, drug designing, right? Actually trying to do the portfolio predictions of the large astronomical problems and all these things. Right, generalization is obviously one of the important aspect. How we will do generalization and interpretability in the quantum, which is far higher than the present present ML level of generalization and explainability, right? How we can bring those two. Those are some of the things which are there. Okay, large data intensive protocols, high dimensional vectors into quantum state, right? Due to the limitations of error and the number of qubits is still a challenge, right? And obviously the noise resilience, okay, right? Hardware management of the hardware noise and right advantage. So yeah, so it is a that means though I am a very prolific a researcher in quantum, but I am not a blindfolded supporter of quantum also. It is not that I will tell that, okay, that means try to do everything quantum from today. It's not like that. Okay, it should be properly understood, and we all hope that there will be a good number of problems where we can suitably plug the quantum acceleration to the classical, right? And once we understand this game of classical and quantum well, I think we can actually solve many of the good problems, and we can make our computing computing performance higher and higher. Ultimately comes under HPC. Quantum is also under high performance computing with the quantum accelerator, but we have to understand well that how we can achieve that. Okay, so I hope that these are good references on quantum machine learning, most probably, because other references are very, you can search, you can get, right? The Deutsch, Joyce, and the Grover's algorithms. Okay. Yeah, so this is something coming on the, yeah, that means I have a sequence of this. So this is coming on the 5th of this month, 5th January. That means a day. That means a day after. So we proposed a tutorial in the VLSI Design Conference. I think this is a very well-known conference. So both Ritojit is not my PhD student, but he walked in the PhD in my that means with me, right, with my PhD student, and he's also I think maybe the second last student of my supervisor, Professor Sushmita Shurkole. Devashmita is also I think maybe the last student in quantum computing under my that means under Sushmita and Professor Sushmita Shurkole's supervision. So she has also worked with me a bit. But now we three are, that means these are my students actually in that sense. But they have proposed a tutorial and they requested me that if I can join them. Okay, so I'm very happy to join them in this tutorial, and that means if you are there, you can be. This will be mostly, that means on the IBM Qiskit, because this is, I think, some way supported by IBM, this tutorial. Okay. Yeah, thank you. And any questions?
Any questions in the chat?
Yeah, any questions in the chat? Yeah, now we can display. Yeah. Okay, so I can. Yeah, please do it. Please do it. Yeah.
This one. So maybe the read out.
So there's a question from Soumita.
Uh-huh.
How do quantum algorithms improve the feature mapping and learning processes compared to classical kernel methods in machine learning?
Okay, very good question. Yeah. So first of all, you can encode the feature space using a lesser resource, right? That I think is very obvious what I lectured here. Okay, so you can encode a 2 to the power n data space using n qubit resource. This is the first. Second thing is that when we apply the kernel, the functional parallelism, right, in a quantum, if we can hold that feature space of 2 to the power n basis states, okay, the kernel, you know, that means, okay, kernel operates on the feature space, and normally the kernel operates on each of the points in the feature space, right? That means one after another in a classical. That means, or you can do it in a parallel computing also. You can do it parallelly. In the quantum case, it is very obvious that you can do it, right? You can do the entire functional parallelism on the feature space, and you can apply the kernel as a functional parallelism to functional parallelism to the entire feature space 2 to the power n basis feature space, right, concurrently, right? And you can generate that particular output of the filter also at one shot. Okay, now the question comes that how we can sample the output. Now, to sample the output, you have to use a measurement procedure, Okay, right? You can use a fundamental operation like a Grover's amplitude amplification, which can actually the marked states in the oracle can actually can be taken out with with those Grover amplitude amplifications, right? Or you can do some sort of tomography. I didn't discuss tomography here. Okay, right? There are things called tomography, right? With which you can actually sample the output distribution of the quantum state.
Yeah. So the next question is from Ans Soni.
Mhm.
So he's asking if there's any concept about quantum memory.
Yeah.
Can we
Yeah,
store
so
some kind
yes. Sorry, I didn't mention it that. It is called the QRAM concept, right? As I said, only one clue I gave in the initial part of my lecture is that the quantum RAM itself is a memory and a computing also. Okay, because the qubit storage what I am defining, right, is getting updated through the state transformation which is done on that memory itself, right? And the state transformation logic is defined in that means at the hardware level by the control pulses, and those control pulse, the sequence of control pulse defines a quantum operation. So something is logical, but if we try to compare it with a physical classical computer vis-a-vis a physical quantum computer, fine. So the memory transformation to the control pulse are being done by the control sequence which is mapped for a gate operation. So it is memory and computing together, and the qubit register can itself work as a memory which gets updated. So RAM means which gets updated. So the scratchpad memory of a classical computer is RAM, right? And the permanent memory of a classical computer is something which is the hard disk. In the case of a quantum, the permanent memory obviously will be a classical register. Okay, but the scratchpad thing, and that will be done after measurement of the quantum memory. But the scratchpad memory or quantum RAM is truly the qubit register state. Yeah.
So there's one last one. So Soumita asked before in the Deutsch presentation, and she wants a bit more in-depth explanation about how does quantum approach reduce the complexity of solving Deutsch.
Okay. Yeah. So there are two things what is done. So if you look into the fundamentally, the y XOR fx operation, the y XOR fx operation, this fx is now done concurrently on all the states of x. That you have to take care. Okay, because this y XOR fx, in the case of classical, you have to do fx for each of the x independently. Here we are generating the 2 to the power n possibilities of x, which are represented by an n qubit x, right? And they are all generated, this y XOR fx over a 2 to the power n combinations of x are generated simultaneously, right? And that superposition followed by a convergence, which is an interference also by Hadamard. We are actually converting it to an interference where we are coming to a singular probability, corresponding to the all distribution probability what we have in effect. So there are two things what we are doing quantum mechanically, which is not there in classical. One is the superposition is that evaluates effects over all possible x, step one. And secondly, due to the Hadamard type of gate, we are able to converge the entirely that means the decision, which is transferred to the fast register by in the second operation is, sorry, I missed it, it's a control operation. So with the control operation is the entanglement operation, by which we are actually taking we are carrying out the fx operation though, but it is pushing back some part of the result to x also. So though we are doing y XOR fx, but some part of the result is pushed back to x also, right? So these two techniques, and then the measurement occurs after the Hadamard. which is a sort of interference. So all these things are very unique, which doesn't have anything, that means which doesn't have a direct analogy in the classical domain. Okay, so all these three things helps in the quantum, right, in the Deutsch algorithm. Yeah.
And to further add to the question, so like when in Deutsch, you have decision on n-bit strings.
Yeah.
Like the function is from n bits to n bits, n bit strings to n bit strings. And the only properties we can distinguish is if the function is balanced or constant.
Right.
Can we add another property into it, or even if generalized to all types of sort of functions from n bit strings to n bit strings?
Yeah. This is a good thing. That means I think people have worked on it. So basically that means basically an n-bit string can have n situ operations, right? And n-bit strings can have n situ operations. Okay, so whether we can actually decide on all the operations. Okay, that means at least some of the, that's a good thing. Yeah, we have to check that means whether this at least attempted. Yeah. Actually, what happened is that most of the people got motivated with the quantum search so much. This number problems, the fundamental logic problems might be we have to look into that. Yeah. And that means presently we have presently Stanford has come up with a paper which is basically on deep learning, but they have actually taken the deep learning operations decomposed into some logic function operations, right? And probably I was exploring that probably after we that means transform a deep learning neural net operation to some fundamental logic. They have expanded it to some polynomial functions of logic, okay, to increase the explainability of the deep learning model, right? I was just trying to see that once we express in polynomial form, right? Actually, we have a very very old paper, 2017 paper I have with Professor Ken Regan of SUNY Buffalo, okay, where we shown that this means that there is another way apart from the matrix representation of the quantum operations. We have a polynomial form of quantum representations also, and later Gil Kalai also adopted that in one of his quantum book, okay, quantum polynomial representation. So that may be a possibility that once we have a polynomial representation, because -1 to the power x, okay, of x, this gives a polynomial opportunity of that means of actually functions, right? And might be if we can convert some black box to polynomial functions, might be quantum can be applied. So these are some of the things we need time and we need good students to work out. Yeah, but these are some of the good things we can do. Yeah, further, sure.
So I think maybe you can paste the question. And,
yeah, you can mail me.
Yes.
Maybe you can make a Google directory also, right? Yes. Where we can, all of us can add.
Forum.
That means you can make a Google forum. You can add me. Right? Some of you can answer them directly. Yeah. Some of the questions I can look into. That will be good. You make this consortium working, and maybe we will have some more discussions time to time, right? It's not only me. I think some of you also can push, also can present, right? This will be good. I think this the national level quantum research consortium, yes, or some sort of consortium, C-DAC can spearhead, because C-DAC is the best organization to spearhead these type of things at the national level. That means if it comes to an university or institute, it will be some localized activities which will not actually go in that national level. C-DAC can take this ahead.
Sure, sir, I think.
Yeah,
that's very good advice.
Yeah. National level research meetup or consortium. Yeah, we can have, and that right, and then if someone wants to have some resource in simulations and all these things, C-DAC can provide that, okay, to support those activities.
Yes. So I think with that I would like to thank you, sir. Our actually Lakshmi.
Oh, thank you, ma'am.
So actually, very, very engaging session, and I'm seeing that a lot of people are continuing to listen to you till the very end. So this itself speaks volumes about the quality of session that you have delivered today, and I'm sure a lot of insights all of us have been able to get. And we are very happy also to note that so many registrations have come online.
Okay.
And
Okay.
more than 600
640.
registrations
Okay.
have come. And this is a
Okay.
very encouraging support by all
Yeah, yeah, yeah.
collaborations also. So I think we look forward to collaborations from
Yes,
a
yes,
lot of,
yes. I am a quantum passionate, but I don't push quantum. Okay, that means I don't push quantum. That I'm blindly okay. You have to do quantum. Nothing like that. Okay, but I feel that quantum is something which is good to take over for high intellectual. So sometimes we have the high intellectual demand, na. So when we have tried to go high intellectual demand, you take quantum and try to do something out of it.
So big thank you also to
Thank
our
you all, yeah.
organizers who have taken a lot of trouble since a month.
Yeah, sorry, I was due to
People.
delay of the flight. I
Yeah,
couldn't also
no,
reach on
no,
time, and Amit helped me a lot to be on
But I
time.
think a lot of people they are asking questions. I think we will make it available on YouTube.
Sure, sure,
And
sure,
we will
sure,
put it
Correct.
on our
Put
C-DAC.
it on our C-DAC
Sure.
channel.
Yes.
sure, sure, sure.
That will be very good
Continue
resource.
to have these discussions.
Yes. So
And
good.
we have a small token of
Oh,
appreciation, sir. So,
have you come there? Come there.
Thank you so much.
Thank you so much.
For your time and all your
No,
enthusiasm that you bring. That is very important.
No, I work very. That means I work with a lot of friends in C-DAC, so I'm very happy to work with C-DAC also.